Good day, participant of ICOBAR. My name is Christian Harito. I am a faculty member in Industrial Engineering Department at BINUS University, Indonesia. Today, I would like to present about mechanical behaviors and modeling of nanostructure anode in lithium-ion battery, LIB, enabling low-cost 3D nanostructures in future LIB for sustainable energy storage. This is our team, led by Arief Budiman from BINUS graduate program. This research is a part of PIB research project from BINUS University. I would like to present first about the research background, and then the characterization technique, experimental, and finally, how we propose to make a low-cost 3D nanostructure anode by electrospinning. First, the background. Why we use silicon anode? We use silicon anode because it has high specific energy, high specific capacity. It has been proven experimentally that it has high capacity and high rate silicon-based lithium battery anodes. So we would like to use this silicon anode for the lithium-ion battery. But there is a problem. It has high volume change, which is 320%. This is very high compared to the other materials, for example, carbon, that it has 10%. But we still would like to use this silicon anode because it has very high specific capacity. Why the volume change is will be problematic? Because usually the silicon is made into the thin film or 2D structures. When in these 2D structures, when the volume changes, it will produce fracture. The fracture will lead to the capacity loss of the battery. We don't want that to happen. So we propose the silicon nanowires. This is the magnified image of the silicon nanowires. We would like to study the stress within these nanowires during the charging and discharging of the battery. We study the stress or measure the stress using the synchrotron micro X-ray diffraction. This is the setup that enables us to measure the stress during the charging and discharging of the battery. We use a window that is transparent to the X-ray, so we can directly measure the stress within the battery during charging and discharging. This is the in situ characterization. After several cycles of charging and discharging, we can see there is a microstructural evolution within the silicon nanowires observed by scanning electron microscopy. This is the microscopic image. It shows that the wires change after several cycles. That means the bonding and debonding of the lithium ions in the silicon nanowires occurs. This is the stress measurement of the silicon nanowires during charging and discharging. Surprisingly, as the voltage goes, the stress changes from positive to negative. That means the stress is a compressive stress. It's not a tension stress. We don't want a tension stress because it will produce crack. When there is a tension, it will separate the surface and produce fracture. So the tension stress is when the stress is positive. The compression stress when the stress is negative. The compression stress will prevent the fractures from happening. So after succeed with the 1D nanostructures, we would like to continue to the 3D nanostructures, because as we all know that 3D nanostructures has a very beneficial properties. For example, it has much larger surface area. That means it can absorb more lithium ions and dissolve the lithium ions much more compared to 1D structures. It will lead to the faster charging rate of the batteries. Efonix has made the 3D nanostructures of silicon using a very expensive method. Well, they know this is very beneficial for a battery, so they pursue this method. But in this research, we would like to propose a low-cost ideas, a low-cost method to make the 3D nanostructures using electrospinning. Okay, so this is the conventional setup of electrospinning using a flat collector plate. In our setup, we use a parallel plate and introduce the voltage bias within the parallel plate. It can align the nanofibers into one direction. So if we change the direction of the parallel plate, we can produce these structures, and it will lead to the 3D nanostructures. At the top, this is the image of the 3D nanostructures made by Efonix using a very expensive method. At the bottom, this is the electrospinning method. This is the nanofibers made by electrospinning method. This is the low-cost method to make the 3D nanostructures. We have made the 3D nanostructures using polymers, polycaprolactone, and polyphenol alcohol. We have also made the 3D copper oxide anode by electrospinning to be used in a battery and test its performance. But in the future, we would like to use this low-cost electrospinning method to make the 3D carbon nanostructures, or maybe even 3D silicon nanostructures that maybe it will compete with the Efonix one. So in conclusion, we have shown experimentally that the nanostructures will prevent the crack, will reduce the stress. So the nanostructures is very beneficial for this anode. Next, we also propose a low-cost method to make a 3D nanostructure anode. Which is in the future, we will use the carbon or maybe silicon materials to make a 3D nanostructure anodes by electrospinning. At the end, we would like also to thank our funder, collaborators, and other experimental support. Especially, we would like to thank the PIB Research Fund from Binus University for their financial support in this research. Thank you very much for listening.